Good afternoon and welcome to my project where I have implemented a simple blockchain using Python. Today we will be looking at the code for the project, followed by a demonstration of how the code works. And finally, we will be using an API to interact with the blockchain. Here we have the Python files which were used to create the project. We have a block.py file, we have a blockchain.py file, and an API.py file. Starting with the block file implements a block class that is used to create block objects. Each block object essentially stores data for us. It includes a block number, transactions to be held inside the block, as well as a previous hash and a nonce. The previous hash is particularly important as this is what makes our blockchain immutable. Every single block contains a reference to the block that immediately preceded it. And this makes the blockchain immutable, as if we were to change the hash of a particular block, we would have to then recompute the hashes of all the blocks that follow it. And this is very computationally expensive, as we will see. So we pass this data into our block object. And in doing so, we also create a hash ID for the block. The hash ID for the block is obtained using the SHA-256 hashing algorithm, which is in fact used by the blockchain network and results in a 32-byte value. This SHA-256 algorithm is used in mining a block. Mining a block is essentially obtaining a hash value for the block that we subject to certain requirements. To calculate a regular hash ID for the block, we can pass the block's attributes into the SHA-256 algorithm. In this case, we pass in the attributes as strings, which we encode to UTF-8, resulting in a hash value from the algorithm. However, we want to make mining the block computationally expensive. Therefore, we say that while the hash ID of the block in hexadecimal is greater than 2 to the power 256 minus our difficulty requirement, we recalculate the hash value of the block. And this is done by incrementing our nonce by 1 each time. We then ultimately obtain a hash value that meets our difficulty requirements, and we set this hash value to be the hash ID of our block. And thus we've successfully mined our block. The final method in the block.py file is a string method, which essentially prints out the block, including its hash ID and its block number. Moving on, we have our blockchain.py file that implements our blockchain object, which is an object that stores our blocks. So when instantiating a blockchain, we set its difficulty, which is the difficulty requirement needed to mine blocks, as we just saw. We also set a chain, which is a list that holds the different blocks. We set transactions as a list of transactions that are yet to be included in a block. We set the nodes of the blockchain, which are the different nodes that send transactions as well as mine blocks on the blockchain. And finally, we create the Genesis block. The Genesis block is the first block on the blockchain that is immediately created when the blockchain is instantiated. So to create the Genesis block, we create a block object with a block number of 1, calling it the Genesis block, as well as setting a dummy previous hash, as we don't actually have a hash value before it. We then mine this Genesis block and append it to the chain of the blockchain. So how do we add transactions to our blockchain? We do so by using the add to transactions method that takes in a sender, a recipient, and an amount. It then places these values into an ordered dictionary. and then appends this ordered dictionary to the transactions list. We then mine the transactions by checking to see if the transactions list is not empty and if there are any pending transactions. If there are, we pop the oldest transaction and delete it from the transactions list. We then use this transaction as the data when instantiating a new block. And this block has a block number being the length of the existing blockchain plus 1, as well as a hash ID of the last block on the chain. We then mine this new block and add it to the blockchain. When we want to add a block to our blockchain, we first want to check whether the block has undergone proof of work. And proof of work is a method that essentially checks to see whether the hash ID of the block meets our difficulty requirements, i.e. the block has been mined appropriately and has undergone the computationally expensive process of mining. And also we want to check whether the previous hash of the block matches the hash ID of the most recent block on the blockchain. If this proof of work is satisfied, only then do we append the block to the blockchain and print out a success message. We can also use this proof of work method to validate our entire blockchain. We do this by cycling through all the blocks in the chain and ensuring that the proof of work has been done appropriately. And if so, we return true, and if not, we return false. Finally, we have our string method that cycles through all the blocks in the chain of the blockchain and prints them out one by one, including their hash ID and their block number. We can now run a quick demonstration of our blockchain through the terminal by running python main.py, which essentially instantiates our blockchain for the first time. So here we can see that the blockchain has been instantiated, and we have added our Genesis block to the blockchain with a appropriate hash ID, as well as the block number 1, indicating that it's the first block in the blockchain. We can now add transactions to be included in a block, which is then added to the blockchain. For example, we could say that James sends Anna an amount of 5. So here we can see that we now have our new blockchain with 2 blocks, the first block being the Genesis block, and the second block being the transaction that we just entered. We can do another transaction for illustration purposes with Justin sending Rachel an amount of 2. So this block has also been successfully added to the blockchain, and we can now see the 3 blocks on the chain. At this point, it's important to reiterate how these 3 blocks are related again. So each block contains a reference to the hash ID of the block that immediately precedes it. So block 3 points to 2 and block 2 points to 1. Additionally, the hash ID of the previous block is used to calculate the hash value of the existing block. This makes the blockchain secure as it essentially becomes immutable. Additionally, we could see that there was a tiny amount of lag between the mining of each block. We could increase this lag by increasing our difficulty level when instantiating our blockchain. But essentially what this lag represents is the computer taking time to calculate an appropriate hash ID value. This is an important safeguard, as when we have multiple nodes on the blockchain, suppose we have a node that wants to change block number 2, it would have to change the data of the block and recalculate its hash, but it would also now have to recalculate the hash of block number 3 and so on. So this becomes extremely computationally expensive, especially as the blockchain grows ever increasingly long. And so this is an important safeguard. So now we can interact with our blockchain using an API. We do this by using Flask. In this API.py file, we instantiate a blockchain with a difficulty of 20. We also create a blockchain node, which is a unique string that identifies the node that's connecting to the blockchain through the API. We also set up a number of routes which help us interact with the blockchain. The first important route being the new transaction route. With this endpoint essentially taking a transaction from the client in the form of a JSON with a sender, a recipient, and an amount, and then adding this transaction to the transaction list of the blockchain. We then have the mine endpoint, which is used to mine transactions that are on the transaction list. An important step here is, apart from mining the actual transaction that we have added to a block in mine, we also mine an additional block, with the sender being the blockchain network and the recipient being the blockchain node identifier mentioned previously, as well as an amount of being 1. What this is essentially doing is rewarding the node for mining a block, which is similar to the incentive structures of blockchains like the Bitcoin network, where nodes or miners are rewarded for mining blocks and processing transactions. So our mining endpoint implements this as well and adds this block to the blockchain. We also have the chain and the chain detail endpoints, with the chain endpoint essentially returning a string representation of the entire blockchain, and the chain details endpoint returning the actual chain in the blockchain, which holds the blocks, as well as the length of the blockchain as it currently is. We are now running our API on a local host, with the local host being this IP address. And we can interact with our API by using Postman, which is the app you see here. So it's up and running, and we can submit a GET request to it. And here we have the response of the homepage, which says, welcome to the blockchain. You can use HTTP requests to view the current blockchain, submit transactions, and mine blocks. So we can view the current blockchain by going to the chain endpoint and submitting a GET request. And here we can see that we have our Genesis block with its hash ID and its block number of 1. We can also see chain details, which says that we have this 1 block in our chain, and our current blockchain length is 1. We can now try adding a transaction to our blockchain by going to the new transaction endpoint and submitting a post request. We can submit our transaction in the form of a JSON object, as we can see here, with the sender being Jason, the recipient being Anna, and the amount being 10. We can then submit this request. And here we see a success message saying that the transaction is ready to be added to the blockchain. We can now mine this transaction and add it to our blockchain by submitting a GET request to the mine endpoint. We send it through. And it's taking a bit of time as we know that the proof of work is going on and the appropriate hash ID is being calculated. And here we can see the two new blocks that have been added to the blockchain. We have block number 2, which is essentially holding this transaction. And we also have block number 3, which, if we remember is the block that contains the blockchain reward for the miner appropriately mining the previous block. So if we go to chain and submit a GET request, we can now see all our blocks in the blockchain. We have our Genesis block, our transaction block, as well as our reward block. We now have a functioning blockchain, but we can further improve its functionality by allowing multiple nodes to mine transactions and add transactions to a blockchain. Modern day blockchains operate through the principle of consensus, where the longest and accurate blockchain is used by all the other nodes and is built upon. So we can implement this idea of consensus and multiple nodes through 2 additional endpoints. The first endpoint being the add nodes endpoint, which essentially allows another node to be registered and to be tracked. And we also have the consensus endpoint, which takes a look at all the other nodes and finds the longest chain amongst all the other nodes and their respective chains. And if this other chain is longer than ours and is accurate, we then replace our chain with the longest chain. 2 functions that help us with this in the blockchain.py file are the validate another chain function and the findest long chain function. So the validate another chain function takes in a chain of another node and goes through the entire chain to see if the chain is valid and if each block has undergone the appropriate proof of work and whether each block has a previous hash pointing to the previous block in the chain. And if the entire chain is valid, we return true. We then have the find the longest chain function, which goes through all the other nodes that have been registered and calculates their chain length, as well as whether their chains are valid. And if we find a chain that is longer than ours and is also accurate, we then adopt their chain to be our chain. And we return true if we adopt a chain, and we return false if we stick with our existing chain. Let's now see how this would work. We have our blockchain from earlier with these 3 blocks in the chain, the Genesis block, our transaction block, and our reward block. We can add another transaction to the chain if we wish. We can do that by adding this transaction with the sender being Sally, the recipient being Abby, and the amount being 2. So we can do so by sending a post request to new transaction with this transaction, and we send it. And the transaction is ready to be added to the blockchain. We mine this new transaction. The block is being mined. This sometimes takes a bit long because of the hashing algorithm. And we can see that we now have these two new blocks, block number 4 being the transaction we just sent, and block number 5 being the reward for mining this block. We can now view the chain again. And we can now see that our chain consists of 5 blocks in total. We can now see how consensus works by creating another blockchain instance that is running on port 5001 of our computer, with the previous blockchain instance running on port 5000. So port 5000 has these 5 blocks, while port 5001 has a blockchain that has been only just instantiated. And therefore, if we look at the chain on port 5001, we see that it has only 1 block, with this block being the Genesis block. So we can implement consensus by looking at all the other nodes on the network from the perspective of 5001 and seeing if a chain exists that is longer and accurate, and if so, adopting it as ours. In this case, the chain that exists on port 5000 is indeed longer and accurate. So we can start building upon this chain by adopting that chain as ours. So to do so, we would first have to register the other node on the network. And we do this by submitting a post request to the add nodes endpoint and submitting the IP address of the other node as a JSON. So we click send, and we see a success message saying that we have added another node on the network. So now this node knows that the node at port 5000 exists. And since the node at port 5000 has a longer and accurate blockchain, we can adopt that as ours by going to the consensus endpoint and submitting a GET request. So when we click send, we see this message saying that our chain was replaced by another longer chain. So now if we go to our chain and submit a GET request, we can now see that our earlier chain, which consisted of only the Genesis block, has now been replaced by the chain of port 5000, which has 5 blocks. And we can now build upon this longer and accurate chain, and therefore consensus has been achieved. That was all for my presentation. I hope you found it interesting. And if you have any questions, please reach out to me. And thanks for listening.